Alrighty, so the thermodynamics of mixing. So I'm not going to spend a lot of time deriving these equations here, but what I do want to talk about with respect to ideal gases, this is going to create our basis for understanding the thermodynamics of mixing. And when you mix ideal gases, it is, I can't write. It is always spontaneous. Right? So think about that. If I have a cylinder of oxygen and a cylinder of nitrogen, and I just both open them up and let them fill a room, they're going to mix with each other spontaneously. So in other words, delta G of mix for ideal gases is always less than 0. And you can actually see this graphed right here. Okay, so I'm going to show you where this equation comes from in a minute. But what's really cool is, again, suppose we're mixing gases A and B, and we then calculated the free energy of mixing. You would actually find it hits a maximum negative value at exactly a 50-50 mixture, which makes good sense when you think about that maximum free energy. And notice here, though, that all of the values are negative, which makes sense. Mixing ideal gases in any quantity will be spontaneous. Okay? So where does this come from? Well, we derived an equation previously, okay, where and this came from the phase changes slides, where I said the chemical potential equals the standard chemical potential plus RT natural log and pressure divided by standard pressure. If you're like, where the hell did that come from? Don't worry about it. I'm not going to hold you responsible for deriving this or anything, but this did come from the phase changes section. Okay. And so now, of course, we recognize then that free energy, right, as we just discussed, is going to be mu of A times N of A plus mu of B times N of B. And now we recognize that I have an equation for chemical potential, which I could supply into each one of these. And furthermore, we also recognize that delta G of mixing is going to be G final minus G initial. Then what that means is this equation, GI, would give me the initial free energy. Then I could write the final energy, right? And then subtract them, and so on and so forth. And again, I'm not gonna like make you responsible for where this gets derived from. But what we would come up with for an ideal gas. So the book always writes delta mix G, and I don't like writing it that way. I like writing delta G mix. Okay. What we would get is the following. Okay. It would end up being NRT. And actually, in my fall 2019 notes, which I've posted, the full derivation of this equation is available right there if you're curious. Okay. But what we would get is NRT times the following. Chi A, and so I'll remind you, the mole fraction of A is going to be the number of moles of A divided by the total number of moles, okay? And then that's going to be the natural log, so chi A times the natural log of A, plus chi B times the natural log of chi B, okay? And so if we inspect this equation really quick, we note that because these mole fractions are always less than 1, right? That means my natural log is always going to be a natural log of a number less than 1, which gives me a negative. So this equation will always be negative. So mixing ideal gases is always spontaneous. Okay. So we also recall from our thermo square and our Maxwell relations that the partial of Gibbs free energy with respect to temperature at constant pressure, and then now I'm going to tack in that number of moles, okay, is negative entropy. So from this relationship, I can quickly come up with delta S of mixing gases, right? And so that's just going to be given by now taking this equation with respect dt, so taking the first derivative with respect to t. And of course, there's a negative sign in there. So then that's going to become negative in r. The t drops out because I'm taking the derivative of this equation with respect to t. And so now that just becomes negative in r chi a, natural log of chi a, plus chi b, natural log of chi b. And a quick inspection you'll realize that this equation is always greater than 0 because of the same relationship here of these mole fractions. The natural log of a number less than 1 is negative, but now I have a negative sign right there, so negative negative gives me a positive. And then this is what we would see for entropy. We would see always a positive value, and again, we remember that criterion for spontaneity. Free energy has to be negative and entropy has to be positive. And similarly, we would also see the maximum entropy occurs when the mixture is 50-50. Okay? So then now, what about delta H of mixing? Well, we recognize that delta G of mixing is just going to equal delta H of mixing minus T delta S of mixing. So that comes from remembering that G equals H minus TS. All right? And if you think about this, if I were to plug this in for delta G, right? And I were to plug in this for delta S, well, look what's going to happen, okay? They become equal and opposite, and the result is delta H of mixing an ideal gas is always 0, okay? So there's no heat released or absorbed when two things mix. And this is actually going to create our basis for understanding how liquids mix. Okay? So we've established for ideal gases, they always mix spontaneously, and there's no enthalpy change when they do mix. And that is going to allow us to think about what happens to a solution when we mix a solution. Okay?